record our lectures. Well, today I have a very interesting topic, the dusk and dawn of computer architecture. So in the last lecture, we talked about the dark silicon problem, right? And by using the word dark, so dark has different meanings. So first of all, it's black, but on the other side, mentally, you will feel like, okay, it's dark, right? So if I'm saying that your future is dark, what do you feel, right? But dawn is actually a different direction. It's actually the sun is rising up. And so today I'm going to share with you, although it seems like we are at the dark moment of computer architecture, however, it doesn't mean the sun will never rise up again, right? So we will see how the golden age of computer architecture will coming back for in today's lecture. But before we start, I know it has been a great weekend for you, so definitely we should recap on where we were. So in the last lecture, we talked about parallel programming is really hard, not only because of new programming paradigm, not only because the coherence issues, the consistency issue that you have taken care. There are also new problems that introduce that new parallel hardware introduced. So one of the example is that right now with coherence protocol, we have a new type of miss in addition to the traditional 3Cs. And the new type of miss is called coherent miss. And the coherent miss comes from the fact that because different processor cores may share the same block. So it turns out that if one of the core is trying to update a block, the same block, then all others has to invalidate their copy, no matter if it's the same exact variable or the memory address that you're modifying. So that's actually a new issue that you have to deal with. So sometimes, and if you are working on assignment 2 already, you see sufficient amount of examples how parallel programming can make your program slower and accelerate your application with parallel cores is not as trivial as you can ever imagine. So for this particular case, you see the right-hand side. Well, it seems like both left-hand side and right-hand side, they look the same. And the left-hand side is probably seems to be more naive and evenly distributed. However, the case is that the right-hand side is faster, right? And also, sometimes you thought in single-threaded programming, we have the assumption that programs should always behave as what we would imagine. However, in multi-core environment, because there are too many non-determinism when you are running your code. So it turns out that for this two threads execution, it turns out that all outputs are possible. And we bet programmers want the fourth one. However, as our demo shows, the fourth one is actually the most difficult to achieve because a lot of different issues. And one of the issues is that, well, so first of all, right, we hope the code could run like this. However, most of the time, because the thread scheduling, we would prefer to schedule one thread launching ahead of time and the other thread launching later. And because this is a really short thread, so it turns out that most likely the case is that one thread finishes execution and the other just started, right? And sometimes, even though we have interleaving execution, the out of order scheduling is going to kill us, right? So there are lots of reasons why you won't get your expected output. So that's why nowadays programming is so difficult, especially at the level of system level. So here's my takeaways, that things that you should always remember is that processor behaviors are non-deterministic. You cannot predict which processor is going faster. You cannot make no assumption when operating system is going to schedule your thread. And cache coherence only guarantee that everyone is going to see the same. However, it doesn't tell you when and how they would evolve to the value that you will see at every time. And to support the update in the order we want, you need consistency protocol. However, if you want to faithfully support total consistency, then it's going to kill all your parallel performance. So it turns out that we can only support relaxed consistency, and even with relaxed consistency, as you can see from our demo, it's very difficult to support. And then we talk about it's not the Moore's law is dying, but the Dinadian scaling is dying, right? So it turns out what happened is that most of the time, if you don't increase the power budget of your chip, you can only have half of them on or the other of them off. So that's what we call dark silicon problem. Or another way you can see it's a dark silicon is that, well, we have to lower the frequency of your chip so that everyone is running slower. So that's where we are. And even with NVIDIA hardware, you can see clearly that they are cheating the performance by increasing the power significantly. The latest H100, you need 700 watts to power a single GPU, which is almost impossible to fit that guy on your desktop computer or laptop computer. So that's where we were now. And however, in the meantime, we have to address the demand of explosive growth of your AI demand. So let's see how we address that. And today, the main topic we are going to talk about is the golden age of computer architecture. So right now, we are in the era of dark silicon, and we want to see how we actually support the demand of application in this dark silicon. So after observing the recent trends, I have 4 different observations from what I can tell. So the first one is that right now your hardware has more and more aggressive dynamic voltage frequency scaling. And the second thing is that when we design stuff, we are focusing on throughput instead of latency. And then sometimes if you cannot address a problem, just live with it. So the third trend I will see is that sometimes we just let it dark. And the last thing is that we try to make our circuit more domain specific. So these are the 4 trends that I observed in the dark silicon era. So let's dive into each trend today. So the first one that I have been seeing is aggressive frequency scaling. So modern processor, if you ever try to do LSCPU as you have done, or even though you look up the data sheet of your processor, you will easily find that in the past, when we say CPU frequency, it's a fixed number. But right now, there is a huge range. So for this particular processor, if you do this LSCPU on your Linux, you will see its minimum frequency is 800. However, it could go up as high as 5,000, right? So that's a huge range. And if you check this data sheet, it also tells you that the same processor can go up to 5 gigahertz, right? And they also have different values for the frequency. So why we see that? And the reason is because, right, as what we learned in the last lecture, so the dynamic power actually has a factor related to frequency, right? So if you lower the frequency of your chip, you can get linear relationship between your power and the frequency. So this is a very efficient way of reduce your active power. And but is it always good for the end? Is it always good for the sake of our purpose? So let me have a quick demo on this. Okay, am I getting this right? Is the right one? Okay, this is not the right one. Okay. Let me see. I should have a demo for this. Okay. Okay. Give me a second. Let me launch an instance of this. Okay. Okay, maybe I can just do demo here then. Okay, so what I want to show you is this, right? So right now, let me, uh, okay, let me log into one of my machines. And um, so here I have a script, which you might already see how it works, is that I have a script that lowers the frequency using some of the programmer technique, and I have a script that tries to lower the core speed of every processor. And in the meantime, I also have a script, this one, is that I try to use this liquid performance counter to get the energy number and see what's the energy number we got for running applications in different frequency. So I would start by putting the processor at the lowest speed and then restore it to all the way to the max speed. So in this way, you will see how that would affect the power and energy and performance of your code. And what I want to show you is actually the program that I'm trying to test is actually one thing that you're familiar with the most, which is our lovely friend matrix multiplication. And this is the block matrix multiplication. So I will run it for twice, right? So right now you see I dropped the frequency of all our processors to 800 and then raise it up to 4.6. And let's see what we got. So when I run it at 800, here is the stats, right? So the total runtime is 22 seconds or something. You don't feel that long because it's aggregated. So it's 22 divided by 32. This is a 32-core computer. And then you can check the energy it consumes. So the energy here, it says, is 26 joule. And the power is actually 38 in total. So that's what we got when we are running at 800 megahertz. So right now, if I'm adjusting it to 46, what would you expect? Execution time, longer, shorter? Power, higher, energy. Okay, so here's the interesting thing, right? So let's take a look. So let's score it all the way here. Okay, so here is the power. It's 49, right? And previously it was something like 30-ish, right? So previously it was 38, right? So now it goes up from 38 to 49. And the runtime, it was 22, but now it's only 8, right? So it's 3 times speed up. However, energy right now is only 12. And previously it was something like 20 something, I guess. Previously, what was it, right? Let me see. Yeah, previously it was 27, right? So one thing that you can learn here is that, right? Traditionally, we thought, well, low power is leading to lower energy consumption, and the energy consumption is in fact representing the amount of electricity that you draw when you are running your task, right? But what we end up got is what? It tells you that sometimes you saw lower power is going to save your battery use time, is going to lower your electricity bill. But what I show here is actually the opposite, right? It's actually hurting the energy consumption, meaning that you are going to spend more energy, more cost, more dollars on running matrix multiplication tests because the slowdown is actually increase the power energy consumption of your task, right? So a lot of time people will think about, okay, low power lead to more energy efficient design. That's actually one of the fallacies that people will find, right? So and here is another one that I made, and as you can see, the number is pretty close, right? So higher frequency, higher power. However, you thought the energy should be higher. However, it's actually lower, right? So sometimes you think, well, having my processor running slower would help energy consumption. That's totally wrong, right? That's case by case. Okay, so that's one trend. But one thing we want to say is that, right, lower the frequency, it still helps the power consumption. As you can see here, it was originally 49, goes down to 38, right? So if you are really, if your processor is really hot, right, that's one thing most of companies would do, right? So one interesting example, right? So I don't know how many of you are following closely to the mobile phone processor development. So recently, I think one of the mobile phone vendor, they try to show Qualcomm or MTK has a better design. I think it's MTK's design, and they run some benchmark. And the first 2 minutes, that processor was really great. However, 2 minutes later, the performance is only 50% of the original. And the reason is what? Because now, once we discover the power consumption goes up to the thermal design, we would lower the frequency aggressively to lower the temperature, right? So, and also, right, and that's actually, right, so like Apple, they sometimes does the same thing as well, right? If they figure out that right now, well, so it's probably pretty common in Riverside. So sometimes if you put your mobile phone on your car and if it's outside really hot, right, and at some point you will figure out that my mobile phone is really, really slow and it's not operable until I put it in front of the outlet of my AC, right? And that's also because of the power consumption issue, right? Okay, so the second trend is actually slower but more. So we go back to this slide. So this slide is actually a pretty good slide in a way that it tells you a lot of recent trends. So in this slide, one thing we talked about was actually single instruction heterogeneous computer architecture that with the same area, you can put 2 simpler cores. So, and in fact, in Intel Alder Lake design, they also follow the same philosophy in a certain way that in addition to those performance cores, you also see there is also a part of the processor that we don't talk about is actually this efficient cores. So the Intel Alder Lake processor is actually a 16-core processor by design with 8 joint cores and a small efficient core. And you can see, right, each efficient core is just this small and each P core is this giant, right? And you might wonder why they want this design. And we can talk about this just a few minutes later. And this kind of design is called single instruction heterogeneous chip multiprocessor. So what modern processor would have is that we would have a few high performance cores and a few efficient cores, or to be honest, lower performance cores, right? And they all use the same front end instruction. So for Intel processor, they are all x86 processors. And from the operating system or the programmer's perspective, we cannot really tell the difference among these processors because they are all the same instruction set architecture. So this is the Intel's architecture. And Intel is not the only company that does the same thing. In fact, all mobile phone manufacturers that are using ARM architecture are also having the same design. So ARM called this big little system. So in their big little system, on the same chip, they will have a few big cores and a few little cores. And big cores are those high performance cores, and the little cores are those lower performance cores. So that's ARM's design. And with Apple, they did the same thing, and they also use the same terminology as Intel. As you can see, they have perf core, which is performance cores. They also have efficiency cores, which is the efficient cores, similar to the Intel terminology. So as you can see, right, Intel's processor has performance cores and efficient cores. Apple's processor has performance cores and efficient cores. And mobile phone processors, they also have this big little cores. And here's the fundamental reason why everybody takes the single instruction set architecture, heterogeneous multi-core architecture design is because there is a potential of processor performance reduction. However, why this design is a good design, that's actually something I would like you to tell me after you read the paper. All right, let's see what you guys get. Okay, most of you pick C, but I know that's what you would pick when you don't know what the answer is. So why don't you go ahead and discuss with your friend for another 90 seconds, and let's see what you guys have after the discussion. Go. All right, so let's see what's after discussion. I bet it's probably C still. But what are the two that you guys have in mind? So how about the first one? What do you guys think? Yes or no? No? You need to recompile and optimize the binary for each core architecture to exploit the thread level parallelism in this architecture. Why not? Why you don't need to recompile the code? It's the single ISA design, right? So the single ISA is actually the key, right? So that's why ISA is a very important abstraction, which people don't really want to change. Or if you want to change, you have to be backward compatible to prior versions, because the good thing about maintaining the same instruction set architecture support would allow compiled code to continuously running on new processors without the need of rewriting or recompile, right? And so as long as you have a multi-threaded process program already, this architecture will allow those programs to continue to enjoy the benefit. So definitely you don't need to recompile it. How about the second one? For a program with limited thread level parallelism, single instruction set heterogeneous chip multiprocessor would deliver better than, or at least the same level of performance as homogeneous chip multiprocessor built with older generation cores. So in modern technology, right? So what they would say is older cores are actually efficient cores, right? So are we going to see that? For a program with not a lot of thread level parallelism, it will deliver better than or the same level of performance as homogeneous chip multiprocessor built with older generation cores. Yes? No? No? Why not? So what's the baseline here? What's our baseline here? No, what's the baseline here? What does that mean by baseline? What's our baseline in this sentence? What? No, baseline means the baseline system. Homogeneous chip multiprocessor with old generation cores. What's the improved system? Single instruction heterogeneous chip multiprocessor. Are we going to see that? What does that mean by you have limited parallelism? It's more like a single thread, or say not a lot of threads, right? So if you have a processor with a few performance cores and each performance core is faster than conventional processor, is it going to be faster? Yes, right? Or you can say, I have a few efficient cores, and if even though I schedule all the threads on this efficient cores, you are still going to get the same performance, right? So I would bet the second one is probably right. How about the third one? With rich thread parallelism, a lot of threads, right? Which one would run better? The second one, the homogeneous chip multiprocessor with older generation cores. Why? Because you have more threads, right? How about the fourth one? With rich threadable parallelism. Okay, so think about this, right? So look at this. This is the size of your E cores and P cores, right? If I give you this amount of die area, how many E cores do you imagine we can put on this processor? What? How many E cores do you think we can put on this processor, given the same area? Maybe 32, right? Because it looks like this is like 4 times larger, right? So maybe 32 plus 8, right? 40. Okay, if you have a lot of threads, and currently it's only with 16 processor cores, right? Okay, saying that if I have a lot of threads, it's a program with a lot of threads. Do you think 40 threads would be better or 16 threads would be better? Right, M-DOS slow, right? Okay, but if you are having a program, okay, so now if you use the same area to only build performance cores, how many processors you would think you could fit in? Probably 2 more, right? Maybe 10, right? Then you will get 10 performance cores only, right? So if you have a program with lots of threads, 10 versus 40, who would potentially give you better performance? The 40, right? So the 40 are homogeneous, right? So if you check what the question is asking for, right? It's actually say homogeneous processor with old generation cores or newer generation cores, right? So this is probably like the case with 40 cores, and this is the case with 10 cores, right? So right now, if you put the number 40 and 10 into this picture, can you answer me? Like, do you agree with 3 or do you agree with 4? Which one do you agree? Or agree with both? 3, right? So here's the thing, right? If you have a lot of parallelism, you probably want a lot of cores, right? However, so here's the thing. You can see the strengths of single instruction set architecture homogeneous processor, right? It's actually targeting case 2 and 4, right? So because most of the time, are you going to create a program with rich parallelism, right? For those of you trying to do parallel programming, you know how hard it is, right? And even though I'm able to make my program like many threads, are we going to achieve a speed up, right? If you have locks, right, you probably don't want that many threads, right? So it turns out most of the time, our programs has very limited parallelism, right? Unless you have a totally different processing model. So For the general case, which are the programs with limited parallelism, it's a better choice, right? And even though you have a lot of so this 2 and 3 are correct. However, this is not going to be true for most of the cases, right? So even though the third one is true, and it shows that single instruction set heterogeneous chip multiprocessor cannot excel the idea of having homogeneous chip multiprocessor with older generation cores, I don't care, because most of the time I don't run into this trouble, right? So, to this particular question, it shows the strengths and the weakness of this design. And single instruction set architecture, heterogeneous chip multiprocessor, is not perfect. However, for the most use cases, it's good enough. So that's why the design is neat. And most of the time, we are designing products that fits most people's demand rather than niche markets, right? So that's why that's a design that's widely embraced by most of the platforms right now. And right now, I'm going to show you a demo to tell you why, as a programmer, you should be aware about this big LITTLE architecture. So the platform is Intel 13700. And as you can see, this processor has 8 performance cores, 8 efficient cores. And for the performance cores, they are also hyper-threading cores. So the performance core actually have 8 times 2, total of 16 threads, and on the performance cores, and also 8 another threads on the efficient cores. And let me show you what am I going to do. Okay, so here is the demo that I have, and this is exactly the same processor as we show on data sheet. And now, so the first thing I want to show is that I have this program, and you probably are already familiar with it. It's the histogram program in your assignment 2. And right now, I'm just running a total of 1 to 4 threads on this particular processor and see what the performance looks like. So it's currently running. Does it typically take this long to run it? I saw this was really fast. Okay, let me stop it. Restart from scratch. Okay, here we go. Run it. Okay, execution started. Okay, it takes a while. Seems like. Okay, so this is using operating system to randomly assign the threads to different cores. And the operating system itself has some kind of scheduler. And fortunately, most of the Linux operating system scheduler are smart enough right now, so we can get a look at about how good they are. So as you can see from this figure, with Linux default scheduler with 4 threads, I'm able to achieve up to 1.8 times speed up. And with 2 threads, it's 1.2. So now I'm going to show you one of the programs that's probably useful pretty much useful in your life. That's called TaskSet. So TaskSet is a program that can attach your task to a certain cores on this particular processor. So here I put -C onto 0, 2, 4, 6, 8, 10, 12, 14. That's because these are the processor cores that I know of that are performance cores. And how to know this information, you probably need to dig into the detail from CAT PROC CPU info, because they do have the processor ID, they do have the CPU cores and core ID for you to tell if they are sharing the same core. So for example, this is a processor 6 and its core ID is 12, and you can see like for processor 7, its core ID is also 12, right? So they are actually the same physical core with 2 different threads. And as we learn from the spec, the simultaneous multi-threading cores are actually those performance cores. So you know that for threads 6 and 7, they share the processor ID 6 and 7. They actually share the same physical core. So they are, so one, they are performance core. And the second thing is, if you really want to max out the performance without being disturbed by other threads, you should not schedule 2 threads together on these 2 cores, right? So that's why when I do this task scheduling, you can see I only assign even numbers because every pair of odd and even numbers, they share the same physical core. And up to 14, that's the last even core processor ID with performance cores. So with that, this line of code is basically saying that right now I'm running my task only on performance core. And let's see what the performance looks like. And in the meantime, I also have another set of tasks that are running jobs on efficient cores. And these are the number of efficient cores that I have is like 16 to 23, right? So a total of 8 efficient cores. So as you can see, right, with running threads on only efficient cores, I can also get at most 1.8 times speed up, right? So looks like the Linux operating system is doing a very good job in putting all this tasks on performance cores if possible. However, sometimes if you are short on cores, this is what would happen. So here I'm only assigning my task to efficient cores. And as you can see, right, so the first two, this is the random scheduling, this is the performance core only, and this is efficient core only, right? So I also have 4 different cores of different threads. However, with efficient cores, right now, the maximum speed up you can get is only 1.5 times, right? So sometimes as a programmer, if you are not aware that you have different core architectures, then you randomly use your processor, then this is what would happen, right? And you know, sometimes you can do half, and let's try half and half, right? So that's something I like to do in Panda Express. Okay, so for half and half, right, I have 2 of the performance cores and 2 of the efficient cores. And let's see what the performance looks like. And as you can potentially imagine, right, what's going to happen is that you are going to see somewhere in between efficient and performance only. Okay, so here, right, you can see the speed up is 1.6, right? So it's indeed somewhere in between, right? So that's our architecture. And this observation is actually coherent to the paper that you read. So in a paper, they were talking about the alpha architecture, and it's probably an architecture that you probably don't need to know anymore because it's not even existing. However, the observation is still the same, right? As you can see, if you have more threads, it turns out that even though you are using slower cores, as long as you have more cores, then your performance will be better anyway, right? So that's why if you have a homogeneous processor with the most advanced cores, you are going to hit into the trouble when you are increasing the number of threads with a workload with more number of threads. And here is another figure that we can find, right? We can find in a paper is that, okay, now if I increase the number of threads to up to 2025, right? And this one, which has almost perfect scaling, is actually the processor with a lot of old cores, right? Which which proves the third statement of the previous question, saying that, okay, if I have a program with many threads, very, very high parallelism, then a processor with slower cores are actually going to outperform because the more parallelism I support, right? But in the same area, if you only have 4 cores, then your performance always bottleneck at 4 times speed up, right? So that's why single instruction set architecture heterogeneous chip multiprocessor become a very popular design because it actually play a very sweet spot here. And most of the time, we bet you are not going to have more than eight threads or even more. So that's why this design is embraced. Okay, so for this question, 2 and 3, 2 and 4, they are correct, right? And however, and here is also a proof that, well, exploring more parallelism from the program is the key to performance gain in modern architectures. Even though it seems like those those efficient cores, they are slower per thread. However, as you have more threads, your overall performance is going up, despite they are slower. Okay, so that's actually an evidence of slower but more, right? Okay, so another trend that I want to talk about is actually GPU. So I don't know how many of you understand know the history of GPU, but in the very beginning, right, GPU is called GPU because it's graphic processing unit. The reason why we want GPU is because we want to render the color of a pixel. And to render a color of the pixel, you need to know the light source, you need to know the reflection angle, and you need to know the viewpoint of the observer. And with this, you will see several different vectors like this. And if you want to calculate the value of a pixel, here is the set of operations that you have to perform. So and within this, a lot of them are just vectors. And then this is a sample C code for that. And as you can tell, you probably need to do some normalization first, and then assign some floating values, floating point values, and all you need to do later on is, and for this, they are just doing this vector inner product operations, and then you perform some aggregation to get the pixel value, right? So that's pretty much what you will see in graphic processing, right? So based on the observation of this is what we want for graphic processing, can you tell me, if I want to design an efficient GPU, what's the basic requirement of the GPU architecture? All right, let's see, what do you guys get? Okay, this is a question definitely we want some discussion. Go ahead and discuss with your friend for another 90 seconds, and let's see, what do you guys think? Wait, what's going on here? Hello? Okay. Huh. Okay, go ahead and discuss. This is homogeneous. No, this is heterogeneous because you can see the E core is here. I just didn't picture it. Right. But this is actually homogeneous. Yeah, but how can I tell? It's basically the diphoto. But here I didn't point it out, but you actually have 8 other efficient cores, right? But if you can tell from the diphoto, right, you see the difference, right? Right, because in AMD processor, they don't have this area. Yeah, well, branch predictor or any unit deal with branch. All right, let's see what you guys have. So more of you think it's D. So should we render pixels as fast as possible? Yes. Okay. Do we need a branch unit? Why not? We have very predictable calculations, or do we actually? So here, right? If you check the C code, that's one of the reasons why I have the C code for you. Is there any branch here? There's no branch here at all, right? So this is a pieces of a code that doesn't even have branch. So if your target code doesn't have branch, do you need a branch unit? Not at all, right? Okay, should we contain an array of powerful ALUs and functional units for a rich set of operations? Yes? Why? We are dealing with multiple mathematical operations, but again, look at the code or the mathematics. What kind of mathematical operations that we end up need? That's 3. Right? So we only need very simple operations: multiplication, aggregation, summation, subtraction. That's good enough. Right? Do you need anything else? Not at all. Right? So, right? How about, should we have very large bandwidth? Why? We have a lot of points. Okay. We have a lot of parallelism that you need to support. Right? Okay. So here's the thing, right? Graphic processing unit, don't forget, is originally an accelerator of graphics. So since this is a graphics processor, so when you design this processor, you should think about what's the cheapest way, what's the most appropriate no-frill architecture to support for that purpose. So if you think about that, right, then how fast do I need to render a pixel? So think about this, right? 120 is good enough frame rate for a game. Agree? Can you even tell the difference between 120 and 60? Some of you say yes, some of you say no, right? I'm the no person. Okay, but no matter if it's yes or no, let's say it's 120 frames. per second. You actually get 8 milliseconds to finish rendering a frame. What does that mean? If you only run your LUs at 1 gigahertz, you actually have 8 million cycles to just render a pixel. So, do we want to render this pixel as fast as possible? And what's the consequence of render the pixel as fast as possible? Power, increase the frequency, and what frequency would lead to? Power consumption, right? So what end up as a graphic processing unit? You want a lot of slow cores, but you want many of them. Agree? Yeah, right? So a lot of people will think about, okay, GPU, we use it for a lot of different things, and it's the mainstream architecture we use to train machine learning models. So every LU should be powerful. Its cores should be really fast. The answer is no. Because think about it's actually graphic processing unit, right? We don't need to render pixels faster than we need, right? So 1 gigahertz is already good enough and probably even more than most of the GANs would need. So in fact, most of your GPU cores are not that fast, right? So what do we really want for GPU architecture? Lots of LUs, right? So for example, an image would have 2 million pixels, right? So we have, don't forget, right? Moore's law allows us to get more LUs within the same die area. So we actually want a lot more cores within the same processor. However, each of the processor, they could run slower, and because they are really regular, and most of the time we are processing vector data inputs, right? So all of them run with the same architecture. So, and the other thing is that they are deadline driven and they are throughput oriented, because all you want is that, boom, at a time I want to output that image, right? This 2 million pixels, 2 million results, they all come at the same time, right? And that's also why you want high bandwidth memory, because you want to support that output in the meantime, right? Isn't that very different from your imagination of graphic processing unit? Graphic processing unit is not fast cores. They are actually slow, but a lot of cores. So it's actually, so two of them are correct, the second one and the fourth one, right? But they are actually applying the concept of slower, but more. And here is the modern GPU architecture. So this is the NVIDIA NVIDIA architecture. So for NVIDIA architecture, as you can see, we partition, as you can clearly see, right? We partition the GPU with several disk clusters of this, and each of the cluster is called a stream multiprocessor. And within this stream multiprocessor, they also have a hierarchical architecture. Each of the unit in the stream multiprocessor, they have the same instruction front end. So all of this processor cores, they can only run one instruction on different pairs of data at the same time. And all this processor, they can only run like either FP32, FP64 integer operations or tensor core instructions at one of this at the same time, not all of them at the same time. That's the stream multiprocessor, right? And sometimes CUDA is trying to mess you up with the terminology called thread. But in fact, each thread is actually one of these ALU operations. So in CUDA's terminology, right? Although you can see like this 16 integer units in the same stream multiprocessor, and CUDA will tell you this 16 ALUs, they stand for 16 different threads. However, all the 16 threads, they can only work on the same thing with different inputs data at the same time. That's how they define threads. That's totally different from your original imagination about threads, right? So, but what I want to say is that the GPU architecture is actually an application of slower but more. And so that's actually one trend that we are seeing. Okay, so right now we have seen, right? Slower but more help us to reduce the active power. But don't forget, static power is more significant now, right? How can we deal with that? So live with it, right? So if you look at the programming model of CUDA in using tensor cores, it looks like this. So first of all, if you want to use tensor cores, you have to set math mode first. And the math mode would actually tell you, I want to specifically use tensor cores for the upcoming operations. What that really tells you is that it's actually tell the processor, now you can turn off other cores. Just use tensor cores for the same stream multiprocessor. So what it really happened is that I only use tensor cores at this time, but other cores, they are actually let idle. So they are actually dark in the meantime. So that's let it dark architecture. Okay, the final trend, which is probably the most important trend, is that the rise of ASICs and accelerators. And that's why we call this a new golden age of computer architecture. So if I want to implement this kind of code, right, AI plus equal to AI plus 1 times 20, I just randomly give an example. And if you have a RISC-V processor, you probably need this amount of instructions. So you need 6 instructions as 5-stage pipeline. However, to support this 6 instruction, you probably need to build a processor like this to support all instructions you need, right? However, if today I know my architecture only needs to execute that particular instance that I want to do, like, then we don't need instruction fetch unit. Agree? Because that's the only instruction we need, right? So we can eliminate that, right? And if we know we only do this operation, and this operation only has 2 inputs, right? So we don't need that many registers, right? So we can further shrink down the register file and also eliminate the decoding unit, right? Now, if I'm only doing this plus operation, then we don't need branch like GPUs, right? We just eliminate the branch unit. So the circuit is even simpler, right? And finally, with the simplified circuit, I can rearrange the design by putting new pipeline registers to make it even faster in terms of clock speed, right? If I really want to do that, right? And then the most surprising thing is that each cycle, I'm actually running the whole coarse grain operation that previously we need 6 instructions to do, right? So that's how you see huge performance improvement with application-specific design, right? So one of the application of this a very commercialized application of this concept is actually tensor processing units at Google. So you read the paper of tensor processing unit. Can you tell me what kind of application-specific design tensor processing unit reveals? All right, let's see. What do you guys think? Okay, apparently we need to sync up our reading regarding the paper, right? So why don't you go ahead and discuss with your friends regarding what you have learned from reading the paper, what you know about tensor processing unit. All right, let's see. What do you guys have after discussion? Okay, it's even more diverse, right? So why don't we have a whole classroom discussion? So first one is TPU optimized for highly accurate matrix multiplication. No? Why not? What? It's what? Not accurate in what way? 8-bit data or 16-bit data, right? So why it's okay to do this? Why is it okay that we just have a 8-bit or 16-bit precision? We don't need very complex matrix multiplication. We don't need very high accuracy, right? So here's the thing. A lot of people would think neural networks is something very accurate, very rely on very high precision. But the answer is that people are so tolerable to incorrect inference results, right? Like every morning when I woke up, when I look at my iPhone, right, the Face ID doesn't recognize me, right? For a lot of reasons, right? What would you do? Try a different angle, right? Try to put your glasses on, right? Try to make yourself look better, and finally your iPhone will recognize you, right? Do you feel angry? Not really. Sometimes yes, sometimes no, right? So here's the thing. We tolerate that, right? And like, yeah, I have that trouble since iPhone X, but this is iPhone 16, 15 Pro, right? I still have an iPhone. So it tells you how tolerable I am to Face ID, right? So that's one thing. We are so tolerable to machine learning. So do you really need to be highly accurate? The answer is no. And by not making things highly accurate, you are actually enjoy a lot of benefit, right? So The 16-bit activation measures computes at half speed, computes at quarter speed when both 16, right? It also makes your power consumption lower. And the other thing, which is also very important, the circuit of implementing meshes multiplier are actually only 25% if you can make your precision from 32-bit to 16-bit, because the circuit is actually like 4 times larger for supporting twice of the precision, right? So the same philosophy, right? In the past, the same die area, if I support 32-bit precision, I can only have one meshes multiplier. But if I support only 16-bit precision, I can have 4 times more circuits, 4 times more meshes multiplier, which give you a lot better performance. And again, throughput-oriented design. They don't have to be really at very high speed, so the power consumption goes low, right? And the heating cost will go lower. And if you find a sweet spot between the energy and the power, then you are potentially save the total cost, which Google cares about. All right, so it's not optimized for mesh multiplications. How about dense meshes? Is it yes or no? No, why not? That's not true. The unit is designed for dense matrices, right? So a lot of people would think machine learning is mostly sparse matches. I want to say that's totally not true, right? And don't ask me why, but Google designed this based on their experiences, right? So and in fact, most of the units for machine learning hardware, they are all dense matrix multipliers. So there is a reason why they don't use sparse matches. So a lot of people were talking about sparse matches multiplication. In a lot of cases, from the real practice perspective, I would think that's a good research topic, but are they really useful for real products? Maybe not. And even for scientific computing, a lot of cases, when I observe this input data sets, I find most of them follow the category that they are globally sparse but locally dense. So with that, dense meshes multiplications are still more important than sparse meshes multiplication in terms of algorithm design. And it's more of about if a programmer can map your operations to those dense meshes multipliers. Okay, so it's designed for sparse meshes multiplication. How about the third one? No? What? So is tensor processing unit an ASIC? What I just said about ASICs. So if you look at the design of instruction set architecture in TPU, they are following the CISC design. What does that mean by CISC? One instruction can do a lot of things. So meshes multiplication, it could be decomposed in many multiplications and addition in GPUs and CPU code. However, in tensor processing unit, it's only one instruction code meshes multiplications, and you're done, right? So it actually reduces the IC performance equation. And there's a reason for that, because it allows the hardware to better utilize the PCU bandwidth. Because if you have a lot of instructions that you have to all send to the tensor processing unit, it's actually very time consuming and result in very low bandwidth utilization. So they just make one instruction, one command that does a lot of things. That's TPU. So do you think they are all equally long instructions? No, right? Because it's a CISC design. Question? It's the CPU fits instruction in the TPU, but I think this is still true, right? Because right now on the CPU side, all you need to do is to send TPU that matches multiplication instruction. Right. So it also reduces the total instruction count of the design. What? So for TPU, no. They are implementing a giant matches multiplication instruction. It's pretty much like the ASIC design that we show. Okay, so 2 of them are correct, right? So this is what a TPU look like. And as you can see, right, a giant part of the design is actually a multiply unit, right, and vector unit, and high bandwidth memory, right? So there are many things that we can learn about the tensor processing unit design. And in fact, as you learn from today, right, the landscape of modern computers are actually like this. In addition to von Neumann architecture components, we also have GPUs and also a lot of AI ML accelerators like Google's Edge TPU, Google's TPU. If you have an Apple phone, you have neural engines. And if you have a NVIDIA processor, you also have tensor cores, right? And they are all AI ML accelerators. And if you think about the heterogeneity in your computer is only about this discrete units, that's actually not true. Even with Intel's Alder Lake processor, you will see we also have AI accelerators like GNA accelerators and graphic cores. So actually the world is very heterogeneous. And right now, as you can see, as what David Patterson said in his Turing Award talk is like this. In the end of the dark scaling Moore's law means the architects is where we're going to innovate if you want to make things do a lot better. When it's not going to happen at the microarchitecture level. Security clearly needs innovation as well. If software-only solutions are not going to lead to more secure systems. The domain-specific languages, raising the level of abstraction to make it easier for the programmer also makes it easier for architects to innovate. And domain-specific architectures are getting these factors of 20 or 40, not 5 or 10%. The open architectures and open implementations reduces the effort to get involved. You can go in and like your compiler and operating codes and make enhancements to these devices. And everybody gets to work on it. It's inclusive and democratic. The cloud FPGAs make it even easier for everybody to build things with what looks like custom hardware. And this agile development means all of us can afford to make chips. So as John said. Okay, so maybe I should take a pause of their talk here. But what David Patterson and John Hennessy Bastille want to convey is that the future as a golden age of computer architecture is because every company, including Google, Amazon, Facebook, as those companies are all now building their own custom chips. So as a software programmer, you need to know how to use this hardware better. On the other hand, if you are coming from an E background, it's the golden age for you because right now we need a lot of people designing chips, right? And even in the United States, we have the CHIPS Act, which is trying to promote job opportunities and research in building chips. So the world is changing. If you only know software design, you are not going to get a good job in the future, right? So that's what they say about golden age of computer architecture. And because this is a short course, so I don't have too many chances to talk about this. But if you are interested about the hardware accelerators, how to use hardware accelerators, and if you want to get an experience about programming on AI ML accelerators like NVIDIA Tensor cores, Google's NVIDIA's ray tracing cores, and Edge TPUs, you are welcome to take my course next quarter. And now, one thing I want to do is that I want to talk a little bit about my research. So in the past, as a programmer, we have the ego that we want to program, use the computer at a very high level. For example, use code written in Python. The lowest abstraction we accept is probably C++. But if you hear what David Patterson said, you will probably be sad. Because what he basically says that this is the future, right? You are going to run application at the circuit level, right? So, well, David Patterson, John Hennessy, they are actually the idol of all computer architects. And they are kind of like the god in our area. However, I don't agree with them. So what I observe here is that if you look at the evolution of computer hardware, it's basically going from spatial purpose to general purpose. So I have a dream. Can I make AI, ML, and then accelerators becomes another general purpose hardware on modern computer architecture? And here's the opportunity. If you see all of them, they are all meshes processors. And in fact, a lot of problems, you can make them meshes problems. So like this SQL queries, conventional ways, you are doing a lot of list intersection, memory copy, and make a new table, doing vector operations to get your result. However, if you can think of the problem in a different way, reshape your data into two different source matrices, and surprisingly, all the result you want for this SQL query is just one matrix multiplication, which is accelerated by this AI ML accelerators. And all you need is one matrix multiplications, which AI ML accelerators can do it really fast. So that's my research is about. Like for the tensor processing unit database system, we achieve up to 288 times speed up than compare against GPU. And it can also efficiently process graph workloads like PageRank. And also, matrix multiplication is not the only type of matrix problems. And in fact, there is a set of matrix semi-ring problems. So for example, all-pair shortest paths, they basically have the same algebraic structure as matrix multiplication. All you need to do is to replace the summation with minimum, replace the multiplication with plus, and then you can solve any DP problem with this matrix semi-ring formation. So turns out another architecture paper that we published is called SIMD Square, which we provide a general matrix semi-ring instruction set architecture on existing NVIDIA hardware. And this is actually a project work together with NVIDIA. So what we do is that for each tensor cores, it not only can do matrix multiplication, but other matrix semi-ring operations. And we can get 8 times speed up compared against state-of-the-art GPU implementations. And without that hardware, we agree matrix algorithm has higher complexity, so that's why it's slow. So, but with our work, we can actually make it faster. So if you're interested, talk to me. And final words, as a conclusion, computer architecture is now more important than you could ever imagine. Becoming a programmer is easy, and you need to know, but you need to know a lot of architecture to become a performance programmer. We are now living in a multi-core era, and we are also now in dark silicon era. So you cannot forget those important architectural stuff in there. And finally, as a tradition, I want to take a group photo. So that's all in the front, and let's take a group photo together. Okay, come on, because next class is coming, right? Okay, okay, let's just stand here, right? Okay, this side is better. Okay, that's all here. Can you see all of us? Okay, so this is, okay, if you cannot see. Are we good? Okay, thank you all. All right, so one more thing, sample final, right? I will put this to our slides, and for this Thursday, you're only going to see free answer questions. So one of them will be about branch prediction. One of them will be about scheduling on register renaming processor, reverse caching, which means that I will give you a piece of code and give you the hit rate and tell me what potential cache architecture is. And also think about cache simulation problem. And also latency numbers every programmer should know. Check this website and tell me why you got this number. And other questions for the open-ended open book final, we have multiple choice, open-ended question, and also programming assessment. And for multiple choice, you probably know a lot of them. Again, the slides will be online later. And other open-ended questions, like you have to read this list of papers to answer me these questions, and I give you 4 different problem set. It's a good thinking process throughout the weekend. And also think about this open-ended question, and programming assessment is either one of this, okay? Other than that, thank you all for this great quarter, and don't forget to fill out the iEval, and good luck on your final, and hope to see you all in the future.